Hey everyone, welcome back to the Explainer. So if you've spent, any time at all in the makerspace, you absolutely know the Arduino Nano. Today, we're doing a deep dive into this tiny powerhouse, literally unlocking its power from its foundational anatomy all the way to seeing it in action. It's essentially the compact little board that built the whole modern landscape of rapid DIY prototyping, and I am super thrilled to break down exactly what makes it such a classic piece of hardware.
Okay, let's dive into this. Here is our roadmap for today. First, we'll meet the Arduino Nano itself. Then we'll cover its features and specifications. After that, we're exploring the key components, looking at how it actually works, and finally exploring some real-world applications. Basically, we're going from unboxing the hardware to understanding how to build actual DIY projects with it.
All right, Section 1, Meet the Arduino Nano. Let's just ground ourselves first by taking a look at the physical hardware we're about to deconstruct. Now, what's really interesting about this slide is just how much they managed to pack into this remarkably small footprint. You can see the ATmega 328P chip anchored right there in the center. Because of this incredibly efficient use of space and its direct integration capabilities, it has long been the absolute gold standard base for embedded projects all over the world.
Moving on to Section 2, Features and Specs. Let's look at the actual technical specs that pack so much power into such a tiny space.
The Nano's features are really built ground up for rapid prototyping. It operates on 5-volt logic, which is fantastic because it ensures immediate compatibility with a vast array of legacy sensors out there. It's based on that robust ATmega 32P architecture, fully supports hardware PWM pins for precise motor control, and, this is huge for beginners, you just program it right through the Arduino IDE using a standard USB cable. So absolutely no external programmers are required to get your firmware running.
When we break down the specific numbers for the I/O pins, the Nano really doesn't compromise. You get 14 digital input and output pins alongside 8 dedicated analog inputs. Think of these pins as the board's senses and limbs. They're what allow it to interact with the world around it. That is a massive amount of multiplexing potential for your sensors and actuators, all crammed into a sub-2-inch form factor. You can run complex systems simultaneously without bottlenecking your hardware.
Section 3, Exploring Key Components. Let's move to and see how this builds our understanding of the specific components under the hood that make it tick.
At the very center of everything is the microcontroller IC. You can think of this crucial component as the central brain of the entire operation. This 8-bit AVR architecture is the true workhorse of the board. It's parsing your C++ code and manipulating the I/O registers in real time, and honestly, everything else on the board exists just to support this one specific chip. Next up is the USB port, usually a mini B or micro USB depending on your board's revision. This port handles a really efficient dual duty. It acts as your serial interface for programming the board while also directly providing the power supply. So it perfectly handles both your power and your code all at once.
Then we have the crystal oscillator. This little component provides the clock signal for accurate timing. I like to compare it to a steady heartbeat. Running consistently at 16 megahertz, it ensures that all your operations and timing run perfectly. Whether you're running communication to displays or sensors, this heartbeat guarantees your bitrate stay rock solid. And this brilliantly illustrates the difference between our pin types. On one side, you have your digital pins, which are used to connect and control things like LEDs, standard sensors, and motors, versus the analog pins on the other side, which are fully equipped to read continuous analog signals from more complex environmental sensors. It's the perfect split for handling both discrete actions and continuous measurements.
Which brings us to Section 4, how it actually works. Let's transition to the programming side and see how giving this brain instructions is actually a straightforward process. It's basically an incredibly simple 3-step sequence. First, you write your code in the Arduino IDE. Second, you just upload it to the Nano using that USB cable. And third, the microcontroller executes the program and instantly starts controlling your connected devices. That's exactly how your code travels from your computer screen right into the physical execution of the microcontroller. It is rapid prototyping at its absolute finest. Finally, Section 5, Real-World Applications. Let's shift our focus to the final destination and explore what you can actually build once you master this simple workflow. Because of its tiny footprint and high reliability, the applications are just endless. We're talking robotics, home automation, massive IoT projects, complex sensor interfacing. You'll even find them running line follower and maze-solving micro-robots.
It is the hidden brain inside countless DIY electronics projects. Fun fact, these robust little boards have even found their way into early satellite prototypes. Basically, if you can fit it in a 3D printed case, the Nano can probably run it.
So, the crucial point is understanding the overall advantages of the Nano. It's incredibly easy to use, it boasts a super low cost, its small size is unmatched, and it's compatible with basically any sensor or module out there. But without a doubt, its biggest advantage is the massive open source community support behind it, making it the ultimate tool for engineers and hobbyists alike.
We've unpacked the anatomy, the specs, and the immense potential of this classic board. The Arduino Nano makes building electronics easy. So, what will you build next? Seriously, I challenge you to grab one and start your very own DIY electronics project today. Thanks for hanging out with me for this explainer. Keep experimenting, keep building, and I'll see you in the next one.